So now you see the results of the positive coated capillary. So in that case, we have a positive capillary. We obtain a positive surface net charge in the capillary. Then we reverse the electro-osmotic flow. Then to continue to see the composition, to detect the compound, we need to reverse also the anode and the cathode. And you see now, this is the positive pole here and the anode here. So if I have the separation of my compounds, I see that now the anions come in this direction, in that direction, so in the cathode, and can be detected because the electrophoretic mobility of the anion and the electroosmotic mobility have the same size, the same direction. For the neutral, this is always the case. No separation, only the detection of all the neutral compound at the same time. And in that case, this is the cation. We can possibly separate or detect it depending of the nature of the value of the electroosmotic flow and the electrophoretic mobility. In all cases, the apparent mobility is is equal to the electrophoretic mobility plus the electroosmotic mobility. And in that case, we have first the anions, second the neutral compound, and third the cations. So here is the final idea about the separation in positive coated capillary. So we know that this is in positive coated capillary, and then we have a reverse IOF, a reverse mu EO electroosmotic mobility. What compound will I be able to detect? So first, I am able to detect all the anions because the electrophoretic mobility and the electroosmotic mobility has the same direction. So the apparent mobility is positive, is less than 0. And then we have the detection. You see here in the schematic representation that we have the detection. Concerning the neutral compound, the electrophoretic mobility is equal to 0. Then the apparent mobility is equal to the electroosmotic mobility. Then we have a detection, but no separation of the neutral compound. And finally, concerning the the cations, in that case, the electrophoretic mobility and the electroosmotic mobility has an opposite direction. And then two cases. The first case is the fact that the electrophoretic mobility is lower than the electroosmotic mobility. Then we have the detection. That's the case here. The electroosmotic mobility is higher than the electrophoretic mobility. And the second case is, of course, not the good case, in the where the electrophoretic mobility is higher than the electroosmotic mobility, and then we have no detection because the compound go to the anode direction. So here you have an example of a separation on a positive coated capillary. We know that this is a positive coated capillary because two things. One, the nature of the coated. See, this is aminopropylsilal, which is a positive system. The polybrane, which is positive, and the BCQ, which is also positive. The other thing is that we work here in minus 28 kilovolt, and then if we work with a negative voltage, we are always in a reversed mode. If we work with positive voltage, we are in a normal mode, corresponding to the bare-fused silica capillary. So here we work in a reverse mode, which is a positive coated capillary. We have a total length of 1 meter, 25 micrometers inner diameter, and we work with 0.1 molar of formic acid. So the question is, we have three separation of different compounds. This is a small peptide, small protein with the difference of mass. And here you have the theoretical plate. The theoretical plate represents the sharp peak and the quality of the peak. You see that here we have difference in some value of the analytic of the theoretical plate. Here you see that for the aminopropylsilan we don't have a good separation, because here you have the collision of different peaks. And for the polybrane and the BCQ, this is quite similar, with small differences, especially with the peak 1, 2 or the peak 7, 8. And we see that when we have this information, we know that on the BCQ we have a higher value of the theoretical plate as compared to the polybrane, and then we have sharper peak with the BCQ as compared to the polybrane. So the better separation is with the BCQ as compared to the polybrane. So the last question of this presentation is what are the parameters to optimize the separation? So using the classical capillary zone electrophoresis, we have two main parameters to optimize the separation, and we will see this because these two parameters allow to optimize first the electroosmotic flow and also the electrophoretic flow of the compound. So this is on this part, the improvement of selectivity. So I show you only some part of this lecture, only the migration phenomenon and the improvement of selectivity. Here you have the capillary zone electrophoresis, which is the simplest mode of capillary electrophoresis. I detailed the mechanism previously on the different slide. So we used only the electroosmotic mobility and the electrophoretic mobility. And then now we have to see the factor which can modify electroosmotic mobility. So remember that the electroosmotic mobility is related to the dielectric constant, the zeta potential, which is the charge of the surface, and the viscosity. Then it is proportional to the charge density of the capillary surface, which is the net charge of the capillary surface, the viscosity, and the double layer thickness, which is the phenomena to provide the electroosmotic flow. Then concerning the parameters, the factors which optimize this electroosmotic flow, we have different parameters like the nature and the concentration of ions. So this is the ionic strength, the pH, and also some organic solvent. But I will focus only on the nature and concentration of ions and pH. We have seen that the nature of the capillary is important. We can work with a bare-fused silica capillary, but also with coated capillary, and then in a reverse mode or in a neutral mode. And of course, we have to be careful about the temperature because we work with viscosity. And then if we have an increase of viscosity, an increase of temperature, we have a decrease of viscosity. Concerning now the electrophoretic mobility of the compound, you see that this is related to the charge, Q, and the hydrodynamics radius. And also, of course, the viscosity. So we can see that the pH is very important because the pH can modify the analyte apparent charge, and we need to fix the charge of the molecule. It is impossible to separate the neutral compound. We have the nature of the electrolyte. So of course, we have to be careful about the nature of the electrolyte and the ions in the electrolyte. We can also have some addition of organic solvent and temperature. I will focus on the pH for this part.